Here on Earth, in a few years, inside the machine under construction that I'm currently in, it will be 10 times hotter than the sun. Come with me. Today, I'm taking you to visit a colossal construction site, the largest nuclear fusion reactor in the world, International Thermonuclear Experimental Reactor. An experimental reactor in which we will try to harness the energy of the stars. All while demonstrating, we hope, that it is possible to extract more energy released from the heart of matter than it takes to make it fuse. But before we take a look at how this magnificent machine works, which is 3.5 times heavier than the Eiffel Tower, and which, by trying to imitate the stars, will soon be able to heat matter up to temperatures of around 150 million degrees. I think we should start by reminding you that a universe without fusion visually looks like this. And to understand why, I suggest as a little refresher that we spend 5 minutes at the heart of the sun, at the center of our star, like all those in the universe. It's so hot that matter takes the form of a plasma, which is a state in which the nuclei of atoms have been stripped of their electrons. In this soup heated to nearly 15 million degrees, the nuclei of hydrogen atoms can collide at such high speeds that they occasionally manage to overcome the electrical repulsions that oppose their meeting, and thus fuse to give birth to helium nuclei. Except that the mass of a helium nucleus is always slightly less than the sum of the masses of the two hydrogen nuclei that gave birth to it. By fusion, in other words, to shine, stars don't burn, but fuse. And for it, the production of light always comes at the cost of transforming mass into energy. To understand why this is incredibly interesting, remember that in the universe, the amount of energy contained as potential in an object is given to us by the famous equation E equals mc squared. Now, when you multiply a mass, even a ridiculously small one, by a number as large as the speed of light squared, you end up with an extremely high value. For example, the amount of potential energy contained in just 1 kilogram of matter is comparable to that released by the most powerful volcanic eruption of the modern era. And that's just for a single kilogram. In the case of our sun, every second, 600 million tons of hydrogen, the lightest element in the universe, are transformed into 596 million tons of helium. The missing matter has become an absolutely colossal amount of radiation. Thus, by fusing light atomic nuclei into heavier elements, our star emits into space every second 1 million times more energy than all of humanity consumes in a year. As you can see here, the goal, the ambition, the holy grail, is to take advantage of these processes that transform mass into a colossal amount of energy. Except that we're not going to copy exactly what stars do. Instead, we're going to imitate them and improve on their way of doing things. Because a reactor like International Thermonuclear Experimental Reactor will be, proportionally speaking, much more efficient than the sun, where the fusion processes are favored by the fact that, at the core, the matter is so compacted that 1 cubic meter of the sun at its center weighs about 150 tons. In fact, even in this extremely compressed environment, heated to 15 million degrees, the tiny atomic nuclei have a very low probability of meeting and fusing. And the stars, which are characterized by their immensity, compensate for the rarity of collisions by the considerable volume of matter involved. To put it simply, the core of a star is very, very large. And in the case of our sun, it's nearly 10% of the star's volume that's involved in these fusion processes. That's why we've chosen here to turn to a slightly different type of fusion than the one involving hydrogen, namely deuterium-tritium fusion. I'll come back to that a little later. The thing to remember here is that for fusion between these two elements to occur regularly enough, we're going to have to be much hotter than in the sun and reach temperatures about 10 times those at the center of our star. That's 150 million degrees. And there, clearly, you don't need to be a genius to know that absolutely nothing can withstand such temperatures. The most advanced metal alloys we know struggle to withstand anything above 4,000 degrees. While we're talking about putting in there a plasma that's 30,000 times hotter than the temperature at which all materials in the known universe have already melted. So, how do we keep all of this from being vaporized by the released energy? And by the way, because it matters, how do we control it? And now, I think it's time to take a look at the insane engineering of this machine. To sum up, the trick is to create a kind of immaterial trap in which we imprison and heat small amounts of matter. And to pull off this feat, they've built a behemoth here weighing 23,000 tons. A machine called Tokamak, housing a strange ring-shaped structure at its center. To give you a real sense of the staggering size of the multiple interlocking layers that make up this gigantic machine, which is still under construction, we are going to virtually strip down this colossus. Take a moment to notice the size of the engineers, who remind us that everything here is out of proportion. So at the heart of the Tokamak is a vacuum chamber made of 5,200 tons of stainless steel in the shape of a ring, or giant donuts if you prefer, or if you're a pastry chef. And inside it, after creating a vacuum with powerful pumps, there will be a raw 840 cubic meters of plasma. You know, that soup of atomic nuclei and electrically charged electrons. 840 cubic meters, that's an incredible volume. But what's perhaps even more amazing is that the entire mixture will contain, in total, only a single tiny gram of matter. You heard that right. While at the center of the sun, matter is so compacted that a cubic meter contains several. 150 tons here. It's a gram that would take up the volume of an Olympic swimming pool. And to prevent the infernal temperature of this gram of plasma, heated to 150 million degrees, from vaporizing the machine, the trick is to direct the path of the charged particles using powerful magnetic fields that will shape the plasma. Force the particles to follow circular field lines and thus prevent them from hitting the walls. This confinement barrier is created by incredibly powerful magnets that form a prison around the plasma, whose invisible bars are magnetic fields carefully designed to trap the burning matter in an immaterial cage, keeping it at a distance. Of the 440 blanket modules, each weighing, nearly 4.5 tons. These blanket blocks, which completely line the inside of the ring, are designed to capture the energy released by the reaction. But you may ask, how is it possible for the heat to escape when the heated matter is confined in a magnetic field that prevents it from getting out? Thank you for asking me the question. In fact, in the superheated plasma, the fusion of deuterium and tritium nuclei produces helium nuclei which, being electrically charged, will indeed remain confined in the giant donuts, while 80% of the energy released will escape from the prison. In the form of neutrons, moving at nearly 10% of the speed of light, these neutral particles are therefore unaffected by magnetic fields and can escape from the mixture, swirling, as if nothing happened, to go crash at very high speed into the walls of the Tokamak. Made of tungsten or beryllium, the same element used for the mirrors of the James Webb Telescope. By capturing this highly energetic neutron flux, the shields in the vacuum chamber are exposed to thermal loads comparable to those endured by the space shuttle during its re-entry into the atmosphere, and it's through these walls, heated to several hundred degrees, that the heat is then evacuated. Thanks to the pressurized water that circulates inside and comes out at the end of the line as steam, which can be converted into electricity. Thus, the absorbing panels lining the magnetic cage are not, strictly speaking, in direct contact with the plasma. Heated to 150 million degrees, but still just a few centimeters away from the infernal swirling matter. And so they serve both to protect the rest of the building from the blazing inferno that will take place here, while also acting in a way like sponges, capturing the energy of the neutrons, which is then released as heat. And on the other side of these shields, both on the outer edges of the ring and at the center, are the guardians of the temple. The giant electromagnets responsible for producing the bars of the magnetic prison. Surrounding the entire vacuum chamber, there are first of all 18 toroidal magnets, and each one of them gives you a sense of the sheer size of the machine. Because they are 17 meters tall and weigh 360 tons, which, just to give you an idea, is the weight of a fully loaded Boeing 747. Made up of 100,000 kilometers of coiled conductor wires. Among other things, their purpose is to make the plasma spin around the center at several thousand kilometers per hour, while forcing the particles into a circular and twisted motion of interwoven magnetic fields. And the craziest thing about all this is that all their combined power, although it involves magnetic energy equivalent to that released by the explosion of 10 tons of trinitrotoluene, it's still not enough to prevent the particles from escaping the magnetic confinement. And during the fusion phases, these 18 giant coils are supported by an absolutely monumental backbone. And I'm hardly exaggerating. Because the so-called solenoid magnet, placed at the center of the Tokamak, standing 18 meters tall and 4.5 meters wide, weighs nearly 1,000 tons. This titan of metal and cable is designed to counteract the vertical drift of the particles. And to do this, it will discharge an electric current of 15 million amperes into the plasma mixture. Finally, 6 circular magnets, each up to 24 meters in diameter and weighing 400 tons, along with 18 small correction coils, are responsible for compensating as much as possible for the deviations and deformations of the plasma, so that it doesn't come into contact with the chamber, whose edges are just a few centimeters from the turbulent mixture. Here, one of the greatest difficulties is actually being able to predict the behavior of flows of plasma matter, because we're dealing with the ultimate in chaotic behavior, plasma physics. a field of staggering complexity with its unpredictable mood swings, turbulence, and other disruptions. Extraordinarily difficult to predict instabilities that give researchers and the powerful magnetic fields trying to control them a real headache. And during which, in a fraction of a second, these magnetic fields tear apart and part of the plasma suddenly escapes from its magnetic cage. To use an image, it's like trying to predict the behavior in the next microseconds of a mixture heated to 150 million degrees and spinning at insane speeds. It's a bit like trying to make accurate weather forecasts 10 years ahead in the next valley over. When these disruption phenomena, which are still largely unpredictable and about which we hope to learn much more, occur. The idea here is to use a cannon to shoot neon deuterium ice pellets into the mixture, which by disturbing its nature will almost instantly stop the reaction. It should also be noted, just to add another layer of complexity to this machine, that just a short distance away, roaring plasma is circulating inside. Inside the huge electromagnets, there's liquid helium cooled to less than minus 169 degrees, as we've mentioned, to be able to generate magnetic fields whose geometry and intensity allow us to direct and counterbalance the titanic pressure exerted by particles spinning at hellish speeds. We need extremely powerful magnets. But the problem is that the staggering amount of current required would melt any conventional magnet as it flows through it. That's why we use magnets made of specific metal alloys here, which have the special property that, once extremely cooled, they no longer resist the flow of current and become superconductors. And I have to say, I like the idea that these temperatures close to absolute zero are needed to ignite hell at the center. Finally, just think about it, to add another layer of strangeness to these feats on the edges of the plasma. Despite the powerful magnetic barrier, a few charged particles occasionally manage to escape. And it's estimated that between 4 and 19 grams of the shield are, with each pulse, torn from the walls. Each of them weighs as much as a dead horse. Well, actually no. 4.5 tons, that's 9 dead horses. Here, the problem is less the very, very slight abrasion than the fact that these atoms, if they are not evacuated by the twisted magnetic fields, can end up changing the composition of the plasma. And by doing so, cool it down, then stop the reaction. That's why the fusion products and the elements stripped from the shield, a kind of unwanted ash, are evacuated at the base of the Tokamak. And to be completely thorough, it should be added that, beyond the layer of poloidal magnets, you find 10,000 square meters of thermal shields, cooled by a continuous flow of liquid helium circulating inside, and responsible for protecting the walls of a structure made of 3,850 tons of stainless steel, the cryostat. A second vacuum chamber that contains, nested inside its shell, absolutely everything we've just talked about, while also simply being the largest vacuum chamber in the world. So, to give you an idea of the scale, this is the lid of the cryostat, the lid that will be placed on this structure here, which represents only 1/3 of the total size of the machine. Okay, I think we're starting to get a sense of this gigantic technological marvel. But that doesn't really tell us how we managed to give a gram of matter, diluted in a volume about the size of an Olympic swimming pool, a temperature 10 times higher than that at the core of the sun. To put it very simply, the secret behind Malady Tear's heating system lies in a magnetic field, a gun, and microwaves. First of all, there's the huge solenoid located at the center of the tokamak. It carries a powerful current. And, just like induction cooktops, they excite the charged particles in the mixture until they reach 20 million degrees. After that, to keep climbing the dizzying temperature scale, it's no longer possible to use the power of magnets. Because, once past the critical threshold of 20 million, the resistance of the plasma collapses. The particles that make it up are, in a way, no longer sensitive to these forces to be heated. And to keep pushing up the thermometer, we will inject deuterium and tritium particles into the mixture at speeds of about 3% of the speed of light. These are accelerated using an electric field of 1 million volts, circulating in 45-ton cyclotrons, before entering the plasma launched at full speed, where these newly arrived fast particles will further raise the temperature by several tens of millions of degrees. After that, to push the bar up to the famous 150 million degrees, we will bathe the plasma in a stream of radio waves with an incredibly high vibration frequency. A bit like how a microwave oven would heat up a pizza. Except here, the device that generates these frequencies, the microwave, is the size of a small building and weighs about 90 tons. And the pizza to be heated is in the form of plasma, and already to begin with, hotter than the center of the sun. As a fun fact, you can calculate that the power of the device is such that it could literally cook an entire elephant in less than 3 minutes. Don't do this at home. Don't do this to an elephant, and there you go, it's ready. You've reached 150 million degrees. The particles now have enough energy to overcome the barrier created by electrostatic forces between electric charges, and so they begin to fuse. All that's left is to regularly feed the plasma with raw material by injecting it every second using cannons. About 30mm sized pellets of deuterium-tritium at a speed of 3,600 km per hour. After that, all that's left is to control the turbulence and maintain the fusion reactions. With the goal, ultimately we hope, of being able to reach and then surpass, for the first time in the history of magnetic confinement fusion, what is called break-even. That is the point at which the experiment releases, in a controlled way, at least as much energy as was needed to initiate it. This holy grail with this type of process and with such significant amounts of material has never been achieved before. Consider that the experimental magnetic confinement reactor, which came the closest, managed to return 70% of the injected power for 1 second. While ITER, with its plasma volume 10 times greater, aims to return 1000% of the injected power, all while being able to sustain this feat for 400 to 600 dizzying seconds,
durations
of time that may seem ridiculously short to you, but are actually endless when you think about the behavior of plasma. All of this is absolutely impressive. So, when does it start? Well, in concrete terms, in 2 years, the site should be fully operational. But when you're operating the largest nuclear fusion reactor ever built, you take it step by step. At first, relatively cold hydrogen plasmas will be created inside the chamber. We're still talking about a modest 11 million degrees, just to test the machine and make sure everything is working properly. Then, time will be devoted to studying the behavior of the plasmas, without pushing things any further than that. And fusion, strictly speaking, with its 150 million degrees, shouldn't that only begin around 2035 after that? So the following decade will allow us to validate or not a whole range of technologies and hypotheses. To hopefully then be able to deploy the first industrial reactors capable of providing us with electricity. Because as gigantic as this construction is, with all these mountains of superlatives I've thrown at you, did you see the baby? International Thermonuclear Experimental Reactor remains an experimental reactor, a reactor whose goal is to demonstrate that it is possible to produce electricity in very large quantities with this type of device. And it is only around 2050 that demonstration power plant should be born, a successor 4 times more powerful and capable of producing energy continuously. 2050 may seem far away to you, but I think it's important here not to lose sight of the vanishing point on the horizon. Fusion remains as it stands an energy of the future, a project that is part of a long lineage and is set to last over time. A project for the future, for the long term, and for generations to come. Some people talk about a semblance of deployment in the second half of the 21st century, until perhaps meeting a significant part of the world's energy demand by the end of the century. By the way, I imagine that lately you've probably seen a lot of sensational headlines from private labs working on smaller experimental reactors, often with different approaches. Unfortunately, if we take a step back, these announcements need to be tempered. Because we are still very far from large-scale industrial deployment. And making this kind of statement is, for the private sector, a way to attract attention and raise funds. To paraphrase, I can't remember who said it. For 40 years, we've been told that mastering fusion is just around the corner. In fact, the risk would be to see this kind of energy, which emits almost no carbon monoxide, too, as an immediate answer to the challenge of the energy transition. In reality, and unfortunately, the holy grail of fusion won't be a miracle solution to the problem we're currently facing. Very complex to implement, it probably won't be ready in time. That's why the possibility, although very cool, of one day deploying this technology on a large scale shouldn't be used as a cover-up argument. In fact, the risk would be to believe that mastering the sun's energy will solve all the problems on Earth. So, I like to think that when asked exactly when it will happen, we can answer for our grandchildren. Deep down, maybe that's the most interesting thing about this story. The measured capacity of research projects that go beyond us and whose fruits will be reaped by others, not ourselves. Committee projects whose design, planning, construction, and operation can span several generations are the great works, the pyramids of our time. Scientific research of this scale is perhaps one of the only fields where you can work your entire life without truly seeing the results. A bit like the cathedral builders, the final result. Here, behind every part or technology that allows this gigantic machine to function, there is a titan's work hidden. Feats of engineering, logistics, creativity, trials, errors, thousands of hours of testing, flashes of genius. Here, the study and understanding of the fundamental laws of nature meet the craftsmanship of gigantism and excess, the most meticulous gestures. Pharaonic in its implementation, as in the diversity of specialized skills it requires to mobilize. International Thermonuclear Experimental Reactor is a colossal project that required thousands of men and women to unite their strength and their minds in order to exist. For decades, they dedicated part of their lives to finding the best ways to heat, cool, and confine the plasma. Beyond the petty turf wars. Because around the International Thermonuclear Experimental Reactor project, about 30 nations are pooling their human and financial resources, sharing their scientific expertise, to potentially write together one of the most beautiful chapters in the great book of human history. By bringing to life an ambitious dream by the end of the century to bring forth the energy of the stars from the Earth. And in this sense, International Thermonuclear Experimental Reactor may also help us rediscover a taste for projects of common interest, those where we look together toward futures that seem a bit too distant. And now you're going to hate me. But after this grand lyrical flight, I'd now like to break the mood with two super sexy topics: money and safety. Let's start with the cash. It's a point that often comes up when we talk about things this big and ambitious. On the internet, you sometimes come across people saying that this kind of project is a financial black hole, which I have to say often makes me laugh. The construction cost of International Thermonuclear Experimental Reactor should be around 20 billion euros, with another 5 billion for operations. 25 billion, that's a significant amount. 25 billion is 1/6 of the profits made by the 5 largest private oil companies in 2022. For organizing the World Cup alone, Qatar spent $220 billion, and these 22 billion are spread across all the countries. In Europe, we contribute about half of the budget. The French contribution slightly exceeds 1 billion. That's 15 euros per person. Come on, one last one. Tax fraud is around 80 billion per year in France. So, 15 bucks per person to potentially, one day, have for 1/10 of the cost of organizing a World Cup. A technology capable of providing, at the same mass, 4 million times more energy than chemical reactions like burning coal, gas, or oil. And 4 times more than nuclear fission power plants. I honestly think that's a pretty good deal, just to give you an idea. It's estimated that future 1,000 megawatt fusion power plants should consume about 250 kilograms of fuel per year. While a coal-fired power plant has to burn, to produce the same amount of energy, 2.7 million tons of fossil fuel. All the more so, if it turns out to be deployable, your grandchildren will thank you. Finally, let's say a few words about safety. Let's start by reminding you that nuclear fusion technically has absolutely nothing to do with nuclear fission. The word nuclear simply means that we're dealing with the nucleus of atoms. In one case, fission, we break apart heavy atomic elements, while in the other, fusion, we merge light elements together. In a fusion reactor, since the reaction stops as soon as the temperature drops if the plasma becomes uncontrollable to the point of escaping its magnetic confinement. The walls simply take a big hit of heat, the mixture cools down, and everything stops within a microsecond. And also, the radioactive waste produced by the reactions is limited both in quantity and in radiotoxicity. On this kind of machine, there are 2 types of radioactive materials that are produced. A few kilos of tritium over 20 years, a weakly neurotoxic element with a very short half-life, about 12.5 years. This means that after this period, for a given sample, half of the tritium atoms have naturally disappeared. And then, in addition to this tritium, which in any case is intended to be reused, there are the walls of the Tokamak, which, after being subjected to intense neutron fluxes, will become radioactive. These blocks will, over time, be replaced by mechanized arms. And, once the project is finished, they will be stored on site, where they will remain an immobile problem for several decades before being permanently stored in reprocessing centers. Finally, other residues, known as medium activity and long-lived, will be stored 500 meters underground, where time will gradually render them harmless. In fact, just to give you an idea, even in the worst-case scenarios, imagined by the Institute for Radiological Protection and Nuclear Safety, the radiation doses received at 2.5 kilometers away would be on the order of a few millisieverts, which is close to the doses of natural radioactivity, coming from the rocks that surround us, just like from space, to which we are on average exposed every year. Finally, you can add as an argument in favor of fusion that the raw materials needed for its operation are available in relatively large quantities on Earth. Deuterium isn't really something we're lacking, since this stable element is found in its natural state all around you, in water. In a simple glass of ordinary water, a little more than one molecule out of 3,200 contains a deuterium atom instead of a hydrogen atom. Which means you've been ingesting it, even in small amounts, every day since you were born. So, roughly speaking, to get deuterium, we're set for a small eternity. We just need to extract it from seawater. On the other hand, tritium is a different story, because this isotope only exists in trace amounts in the Earth's environment. As a result, during its operation, International Thermonuclear Experimental Reactor is expected to consume almost all of the world's tritium reserves. That sounds huge, but we're only talking about around 40 kilograms. In fact, one of the clever solutions found to obtain this precious element is to produce it on site. The idea is to insert lithium inside part of the Tokamak's walls. An element that, when hit at full force by high-energy neutrons, will produce helium. And as you saw coming, tritium. And since lithium is relatively abundant on Earth, with this type of fusion, we'd be set for tens of thousands of years. This concludes our visit to one of the greatest scientific, logistical, and technical challenges currently under construction on the planet. A puzzle whose single reactor at the center of the complex required the assembly of nearly 10 million different parts to be built. So, of course, trying to fit everything into one video is a bit frustrating. Maybe I should have. You're talking about the constellation of buildings that spread all around the 60-meter height of the Tokamak building. Of those, for current conversion, the gigantic cryogenic plant, the cooling towers, or even the coil assembly area. So large that you could easily fit a building inside. Like the 5 kilometers of cryogenic lines or the 40 kilometers of cooling pipes that wind throughout the entire site. But the decision had to be made. Another second has passed. And now the sun is even lighter and gets a little closer to the moment when it will start to operate. By unleashing hell in a confined chamber. So that one day, maybe in a very, very distant future, it will be possible to create little paradises of energy, the grandeur of stars in miniature,